As promised, we're going to graph and analyze a parametric equation that's actually a friend that we know and love from algebra class. It just doesn't look like it right now. So we have x is equal to 2t and y is equal to 3t minus 4. All right, so those are new ways of viewing x and y, reviewing them as functions of this parameter t. Now you'll notice that t is restricted. T has to go from -1 to 5. Which is why I have my table going from -1 to 5. I actually skipped the 3 value because I just didn't think we needed every value in there, but maybe I should have put it in, I don't know. So now you substitute these t values into these equations. So -1 times 2 is -2, -1 times 0 is 0, or excuse me, negative 2 times 0 is 0, 2 times 1 is 2, 2 times 2 is 4, 2 times 4 is 8, 2 times 5 is 10. All right, now the y values that accompany that. 3 times -1 minus 4 is -7. -4. 3 times 1 minus 4 is -1. 6 minus 4 is 2. 12 minus 4 is 8. And 15 minus 4 is 11. And now I have new points that I can now graph. So here, when t was equal to -1, I can graph the point -2, -7, which is over here. -2, -7, right there. Then 0, -4, 2, -1. Let's see, 4, 2, 8, 8, which is right here, and 10, 11, which is right here. So I have almost every point, all the whole number points there. Now you don't extend past. This isn't a line. We're restricted by this domain from -1 to 5, which means we really stop here and here. It's a line segment, not a line. It doesn't have arrows on it. Okay. All right, so we've completed the graph. Now we've noted the positive orientation. We haven't put it on the graph yet, but we need to. The positive orientation is saying the direction in which the parametric curve is generated as the parameter increases. In other words, you put arrows on the graph, right? So you start at your first value for your parameter, which in our case was t equals -1. That's the start. And as you move to the end, which direction are you going? This way. So you indicate that with arrows along the graph. That's the positive orientation being indicated. Now let's figure out an equation for what's going on here. A typical equation, aka an algebra equation, right? So if we looked at this in algebra, what's happening? All right, well, let's see here. If x is equal to 2t, that means that t is x over 2. And I can use that fact to substitute into the other equation I have, which is y equals 3t minus 4. So instead of t minus 4, here we go. Instead of putting in t, we could put in x over 2 minus 4, which is really 3/2 x minus 4. And thus, we have an algebra equation, because that's what that line segment would have looked like, right, in algebra class. However, there are a couple other things we would want to put. It's an algebra equation, however, it's restricted, right? We're not going forever, so there's no arrows on this. So we actually want to restrict our domain from -2 for x until 10 for x. So we would say -2 is less than or equal to x, which is less than or equal to 10. Right? That would be part of this. All right, so what have we got? Let's describe this. This parametric curve is a diagonal straight line segment, right? Because it's not a line, because it doesn't go on forever. It's restricted from that moves from -2, -7 to 10, 11. This part is when t is equal to -1. This part is when t is equal to 5. Now, how do I know it's a diagonal line segment? Well, because it has a constant slope, right? Which was equal to 3/2, right? That constant slope means it was a line, which is actually our point for the next page. Because it asks us, what is the slope of the line? Well, okay, again, really quickly. It was y equals 3/2 x minus 4. So therefore, the slope was equal to 3/2. Now, think about what slope is. Slope is change in y over change in x, right? So slope is change in y over change in x. If we think about our equations, it was 3t minus 4 is y, and 2t was x. And so when you look, the ratio right there, 3/2, right, came out of the ratio of the leading coefficients. Now, it doesn't always work that way because this only works this way for a line, but it does work for a line, and that's what they're talking about right here. That if you have x is equal to some linear function, x0, which is a constant, plus a, t, right? A is another constant. So you'll notice x0, y0, a and b are all constants, like that. So if you do have that, then a and y is similarly y0 plus bt, where y0 and b are constants. Then the slope is b over a. And it passes through the point x0, y0. So that means that you can make the equation of a line. Let me just remind you from algebra class. It's called the point slope form of the equation of a line. Y minus y0 equals m times x minus x0. And you can use that to come up with the equation of a line if needed. All right, so let's look at this particular example. We have x is equal to negative 5t plus 2, and y is equal to 6t. Okay, well, let's just analyze that really quickly, because those are both linear, so it's going to be a line, right? That's why I know it's going to have a slope and a y-intercept. So if I look at this, I have a, which is negative 5. I have x0, which is 2. I have b, which is 6, and I don't have a y0, so y0 is 0. All right, so then I know the slope of this equation is b over a, which is 6 over negative 5. That is the slope, period. The y-intercept, well, I can do that a couple ways, but one thing I can do is I can use the equation here, and I can say y minus y0, which was 0, equals 6 over 5 negative, so negative 6 over 5 times x minus, well, x0 is 2. And I can use this to find the equation, or to find the value for the y-intercept, because the y-intercept is 0 comma b. So this would be y equals negative 6/5 x plus 12 over 5. So that was really easy. So then the y-intercept is this number right here. Well, it's 0 comma that number. A y-intercept is, of course, a point, so it has to have coordinates. So 0 comma 12/5. There. All right, now suppose the line y equals negative 9x plus 3. Well, suppose there is a line that is y equals, sorry, there's a little typo there. Suppose there is a line. There we go. Y equals negative 9/2 x plus 3. Find a parametric equation for this line. Hint, find a point that it passes through. Interesting. Okay, so there's several ways to do this, but we can think about a couple things. One, we know the slope. The slope is negative 9 over 2, which is b over a. So I know that that one, the a is going to go with the x and the b is going to go with the y, right? So I know it's going to be x equals 2t plus something, and y is equal to negative 9t plus something. And then all I need is a point that it goes through, x0, y0. So if I look at the equation, I notice that it goes through the y-intercept, which is 0, 3. So why not make that x0 and y0? There's nothing special about x0 and y0 other than it's a point on the line. So I can say, all right, then I can say 2t plus 0 and negative 9t plus 3. And there you have it. Now, if you wanted to, you could also use, because of course, how do you know that the negative goes with the 9 and not with the 2? And the answer is you don't. So you could also go x equals negative 2t plus 0 and y equals 9t plus 3. Either one will work. Now, I actually just want to touch on the next page because it doesn't really require much other than noting that you can do all of this with Desmos. I'm going to skip over the calculator because who wants to use a calculator in this modern day and age? It's available in the calculator if you're interested, but who wants to use that? Desmos is so much easier to work with. So, for example, let me show you the problem we were just working with, actually the previous problem, problem number 1. You can see it was 2t and 3t minus 4, like this. Right? And you can establish it's a diagonal line and it's doing all of that. Now, if I want to change it to the one we were just looking at, I can actually prove that it works either way when we were looking at it. So it was negative 9t plus 3 right there. And then I make this negative 9t plus 3. So negative 9b plus 3. Right, when I'm doing this, you don't have to have this extra piece. I just like it. Here, I'll show you. I like it when the point is there and when the curve doesn't exist except for when it's less than b. If I get rid of that, it'll just have that whole piece drawn. And I like having that extra piece because then it reminds me that the function doesn't exist until it's passed through that value. Now, I was saying it would work either way. So if I put negative here and positive here, and then negative here and positive here, it's still the same line. The positive orientation might be different, but because we weren't given a positive orientation for the problem, then it's no big deal, right? So we might have to worry about that if we were given a specific orientation. And that's how you graph. It's really that simple. So you make parentheses, you put in your x of t right there, comma, your y of t right here. You do not need to have this extra piece, but I like it. I'm saying that t is less than or equal to some constant. I put in a slider bar for that constant, and then I can actually watch the graph get built and drawn, which I like. The other aspect is to take that out, and then I still like having this point built off of that constant so I can see the point going through the graph, and that shows me that positive orientation. It doesn't do arrows, it does literally the motion, and I can see that motion with that point. So that's really nice. But me personally, I like adding in this one little component right there, which really shows the motion through the graph. And that's it. That's how you draw. Other than that, it's really pretty. So this is the butterfly graph that's on your notes, and you can see this particular one I actually did not add that code in, so I left it with all of its code right there, and I did not add a component at the end that had the butterfly only exist for when it is less than equal to some value. I did not do that. I just thought it was too pretty. So, but I do have the point swinging through. It's literally the same function for that point. It just has it has a constant a. So I put in some slider constant a, and then I added a slider, and there's the x, and then comma, there's the y. So it's a pretty complicated function, but there it is, and it makes that beautiful curve. And that's how to graph in Desmos. Oh, one other thing. You'll notice the domain is right here. So when you put this in, you're establishing your domain for t. So if you want it to go from -4 to 3, you can do that, right? And I would make, in the case of my slider, I'd make -4 here and 3 here to match if I want to use the slider feature. If you don't want to use the slider feature, then you don't have to. But I particularly like it because I think it helps show the motion of what's happening, right? But of course, parametric equations have a domain for their parameters, so that always has to be put in somehow and some way.